Okay, so where did we get last time? Which is the last things we did? Somebody has the notes? Klein-Gordon equation. We wrote it down explicitly. Okay, so basically what we did last time is we know that there is this relation between the momentum and the energy and the, the various components. Then we promoted this to be operator. And this operator for us is the dx mu. So this, if you want, is a definition. Then this is an operator relation that is IH dd dx mu square ddx mu applied on something, because this is a differential operator, so we apply on a sort of wave function. I mean a sort of wave function, I said, because it looks like a wave function, but there are several stringent limits if we want to give a one-particle interpretation to this. I told you the other time that we cannot, in relativistic quantum mechanics, we cannot localize a particle at a distance less than the Compton wavelength, otherwise it starts producing many other particles. And second, that as there is always a space-time relation between one and the other, we have also a limit on delta t. So that means we should keep that things in mind if we want to interpret this as a system describing a one-particle relation. So now if you work out it explicitly, you get the following things: keep account of the I, keep account of the various sign, and the final result is this 1 over c squared, the second derivative with respect to t2, the second derivative x squared, okay. So if you want, I mean, people can often ask, where do you derive that equation? This is not really a derivation. Okay, we postulate that equation like we postulate the Schrödinger equation. Also, the Schrödinger equation is not derived. What we have to show is that the solution of this equation describes some physical system. And in particular, what we will do now, we will see that if we look at the free particle, so you see there is no potential here, there is only the mass. If we take solution of the following form, exponential minus IH p mu x mu, this is equal exponential minus IH bar p0 x0 minus p times x. This is the space part, and this is equal exponential IH bar p times x minus e times t. You see that from this plane wave solution, the c has disappeared, and it has disappeared because P0, let's remember here, P0 was E over C, and X0 was C over T. So when you multiply P0 x0, you get that C disappear. This is an important thing. Now, let's see if this, that is a plane wave, you know, it has the usual form of non-relativistic plane wave. Let's see if, so this is, when you do also Schrödinger equation, you take solution of this form. Let's see if they are solution, okay? You remember that these are solution in the Schrödinger equation if p squared over 2m is equal E. Let's see here if they are solution always or P and D are constrained. When plug that in, okay, so plug that in and do all the various derivative. And what you get is the following things. From here, you get E squared over C squared minus P squared minus M0 square C square psi equals 0. Okay, so this derivative, second derivative, pulls down from there this expression. So you see that is a solution if this is identically satisfied. But this has that form and is not identically 0, this psi xt. So to P0, this part has to be 0. That means A squared over C squared minus P squared must be equal to M squared C squared. Maybe I lost something, no. So that means a plane wave is a solution of the free Klein-Gordon equation only if the energy and the momentum satisfy this mass shell relation. Now, let us look a little bit at this in more detail, and let's see, let's solve it, and let's see, for example, how many energy we have given a momentum and a mass, how many energy we have. Well, it's easy to solve this. E is equal plus minus M squared C squared plus P squared. So there are two energy associated to each momentum, while in the non-relativistic case, what did you say? Right. C. In the non-relativistic case, you remember that E has a particular form that is P squared over 2m. And so there is only one solution. Given a momentum, there is only one energy. Here there are two. And let's see how they are. And the reason there are two is because, you know, differently than in the Schrödinger equation, here there is a second derivative, while the Schrödinger equation has only first derivative, if you remember. And this is very important and is crucial and is all the matter. Now, as there are two solutions, let's start, for example, with the lowest momentum, P equals 0, and let's see how they are made. Well, they are made in this manner. This is the 0 things. Then here we have M0 square C square, or actually, there is something wrong. C fourth. Now, let me, sorry. I bring on the other side, so I get this, I have put outside, then here, and then when it goes in, it goes, okay. So now, if you look, the energy is like that, is above this threshold and is below this threshold. So it's something like if this system could describe system with negative energy. We will not use this interpretation, even if this is what appears. We will go through it and see, give a different interpretation, even if the energy here is negative. And so we have to give an interpretation to this. And this was all that the problem that arose when Klein and Gordon proposed this equation. Immediately they realized there were negative energy, and usually negative energy are something that you don't like because negative energy are associated generally with potential energy and not with, here there is no potential, and second there was negative mass and so on, so they tried to give a different interpretation. But there are further problems, not only the energy interpretation. Now we will see that the usual probability interpretation is as problem. The usual probability interpretation, you know, in quantum mechanics was that the psi modulo square can be interpreted as probability density, and of course the probability density is always positive. Now let's see here if we if this can have a meaning as probability density. Now let me cancel. So trouble with the probability interpretation. Now we will remember that tomorrow is the last day for the first set of homework. I mean, there are few and easy, and also in the second part there were few and easy, so I'll... okay, so let's write... okay. Let's write the equation as we had before in this abstract form. And let's do the complex conjugate. These are Hermitian, these operators so they don't change, equals 0. Now let's do the following. Let's multiply this first equation by psi star and the second equation by psi, and then subtract the two. What you get is psi, yes? Oh, yes. Let's subtract the two, and we have psi p mu minus m0 square c square psi minus psi p mu. Okay, so these are the two equations. One I obtain as the complex conjugate of the other. I multiply the first one by psi star, the second by psi, and I subtract. It's the same things you do with in the Schrödinger case to derive the continuity equation between the probability density and the current density. You remember that things, okay? So now if you replace p mu, yes, p mu with this operator with IH ddx mu, then this equation leads to the following equation: minus psi star h square the mu plus mc square psi plus psi. There is some, no, the sign are right. I mean, I factor out an overall minus 1 because here doing the square I get a minus. With this minus it compensates, so h square so this is the gradient, the symbol for the gradient, okay, and this one, if you you see this piece cancel with this piece, and if you neglect the h square you get the following equation: the mu psi star the mu psi minus psi the mu psi star equals 0, and these can be written as a d mu j mu, where j mu is equal IH to m0 psi star. Now you can say, how did you get this factor? I got this, I put in by hand this factor. You see, from this, I can get this with a factor in front. There is no, why I put this factor in front that does not appear there, in order to give to this, especially the zero component, the meaning of probability density. Okay. Okay. And the meaning of probability density, it means that if you take J0 and look at this dimension, the dimension is 1 over a length cube, okay, with this factor in front. Yes?
The definition of current density.
Current density, yes.
That imaginary I, if it is supposed to be in the denominator.
The J mu?
The complex I.
The complex sign, the denominator. Well, this book used the definition, if I am not wrong, with the plus.
It went on and it contradicted. So the two definitions that I is. Maybe let us work with it, but.
I mean, you agree that this object is this, so it has an I in the numerator. But it doesn't matter. It doesn't matter where you put, you know, I mean, it has an I in the, you see I have added all these p's, h over 2m, okay? Please. The? Yeah, in fact, now we will go and see which is the zero component. Okay, you see, this is the conservation law, and this is a 4 divergence equation. Now we will go and do the 2 component. Let's do in components, okay? Let's do these in components, and let's see what comes out. It means let's specify the mu. What we get is the following. Remember, x0 is Ct, so take account of all factor of C, and you get d dt I h bar 2m0 c square psi star d psi dt minus psi d psi star dt plus, then I have the space part, because here it contains d0, and then di. Okay, so I have the space part that is a divergence of what? Minus I over h to m0 psi star. This is the normal space divergence equals 0. So this equation in component is this, keeping account of all things. And then you can write this as d rho dt plus divergence of a 3 current. See, this is the 4 divergence. This is the 3 divergence. I put a vector above it. And now let's look at the various rho. Rho is equal, yes? The index is up. But these, oh, you mean I put the index above if you want, yes. But what I meant with the index down, it meant the following, then the index goes up. The reason I put the index down here is not that the index is down, is I meant this, and then it goes up, the index, okay? So it doesn't matter if you, I mean, it depends which is the, so I call this object IH ddx mu, and then I know that the index goes up. So if you prefer that manner, let's write that manner, okay? It's just a problem of convention. I like that all of you are careful to this position of the index and so on, but I hope you don't miss the big substance of the problems, okay? Because I will not penalize you in the final exam if an index is up, an index is down, or plus or minus. I penalize you if I understand that you don't grasp the physics, okay? So don't waste much time on this. I don't myself waste much time, and it might seem sloppy, but I care that, you don't look at this detail and grasp the physics. And now here there is a piece of physics that is extremely important, that is one of the most important of the beginning of last century. Okay, so let me write down the H. And the current is this. Now, from this relation, we immediately derive that the total charge is conserved. So let me cancel this. Did you manage to find the book with no problem? Okay. I will tell you which part we do. We will not do all the book, and even in the Klein-Gordon equation, we will only do some sections. So now we are basically doing, we are basically around page 10, 11, something like that. But I will tell you which section we will skip. Now, from here, it's easy to derive the usual conservation law. How you do? Well, you integrate over d3x. And with over all volumes, so all volume of the system at infinity. Here you use Green theorem and says, well, this is equivalent to the integral over all the surface of J multiplied d sigma, okay? And this is made of wave function that we suppose are normalized. So at infinity they go to 0. Okay, modulo those who are like the free waves, but okay, this is 0. And then this object is basically d dt d3x rho is equal 0. So the total, this is the total probability density, is the total probability, sorry, and this conserves. So this is called continuity equation. And it leads to a conserved quantity, is the total probability. But what is more important is that we look at this. Look at the expression. The expression is quite different from the one we used to have in non-relativistic classical mechanics. If you remember, the non-relativistic one was psi star psi, and it had the meaning of probability density, and real meaning of probability density because it's positive and the total probability is positive. But here there is this minus sign. Not only there is this minus sign, you see it is a second order equation, the Klein-Gordon equation. So you have to specify the value of the wave function, the value of the derivative, as you like at the initial time. That means those two, the wave function and the derivative, are arbitrary. If they are arbitrary, I can cook up things so that this quantity is negative. Okay? And then the interpretation of probability density is in trouble. So that is the most important thing. I mean, people have worked so hard in non-relativistic quantum mechanics to associate to psi, to the wave function, some meaning. We know the meaning is probability density. In the non-relativistic things, everything fits because this is positive, and second, all the experiment fits with the fact that this is a probability density. But here, I have a problem. If I interpret this quantity is conserved. This quantity is conserved. I call it the total probability, and this is the probability density. But there is a problem in giving that interpretation. This quantity can be negative. Okay, so if they tell you which is the main problem with the Klein-Gordon equation, the main problem with the Klein-Gordon equation is not the two energy, that the fact that there is a negative energy. We will interpret that in a different manner, and we will fix that things with no problem. What is really a problem is that we cannot give a probability interpretation to the continuity equation that we derive from to the temporal part of the continuity equation, this row. We cannot give a probability interpretation, and then of course, you know, is a very this is a very troublesome thing. And why all this is related to the fact that the Klein-Gordon equation was a second order equation in t, and then we have to give as initial time the derivative with respect to t, and we are free to give anything we want, because as it is second order in t, we have to give psi, and we have to give the derivative. So Dirac, for example, started working and saying maybe there are other relativistic kind of equation that are first order in t, and that is what Dirac did, and we will go later on to the Dirac equation. Now, the first things that we will do is, as it is being postulated, this equation, well, we know that the free wave satisfies that equation provided P and D have the usual mass-energy relation. But the first things that people start worrying when they realize that there was not a probability interpretation is, has the Klein-Gordon equation the correct non-relativistic limit? Well, it has, and now we will go through and perform those calculations. So let's see if the Klein-Gordon that was postulated, so it might be a wrong equation, because it is for sure Lorentz covariant, because, you know, it has the right the Lambertian, the four de Lambertian, means we could have written it in this manner. And this is Lorentz covariant because this is just, you know, the x mu, so it's Lorentz invariant. And, but as we have trouble with the probability density interpretation, as it the correct limit, it might be that it does not have the correct non-relativistic limit. So the first thing is trouble with the probability interpretation. The second, let's see if we have, well, I can cancel now, I think. You have understood? Now, let's work out what is the non-relativistic limit. Yes?
So, what's zero? I mean, what is the ultimate solution for this problem?
Oh, we will see which is the solution with this problem, that basically we will not interpret this as probability density, but as charge density. And then the Klein-Gordon can describe particle with both positive and negative charge. Okay, that is what will turn out to be. But let's first work out the non-relativistic limit. Well, let's, to work it out better, you know, in a particle that is relativistic, there is a huge mass, a huge energy in the mass part. And then there is some kinetic energy that usually, if the particle is relativistic, it can be as much kinetic energy as mass energy. But if it is non-relativistic, the kinetic energy is smaller than the mass energy. So let's parameterize a generic solution in this manner. I can always do, means nobody forbids me to parameterize the solution in this manner. Okay, that means I have taken out, this is a complex number, I have taken out a phase that is this. Okay, I can always do, this is, if you want, this is the definition of this, given a generic things, and writing it in this manner, it means this is the definition of phi. Phi r of t is nothing else than psi exponential I over h m0 c squared t. So there is nothing, I am not restricting my solution writing them in this manner. This you can interpret as a definition of phi. Phi is like that. Okay, so I am not doing this, I am not restricting my solution to be of some particular form. Now the other thing is, yes? R, yes. Now, let's define the following quantity. The total energy of the system minus mc square, m0 c square. This is sort of the kinetic energy. And as we are working, we say no relativistic limit. So that means the particle is not going at the speed of light, it's going at a much lower speed. So the kinetic energy is much smaller than the mass energy. So this one, that is the kinetic energy, this is the total energy. We subtract the mass energy. This is the sort of kinetic energy. The hypothesis that we make is this. This now is the non-relativistic limit. So the non-relativistic limit means for me, because I don't have velocity here explicitly in the equation, I have the energy in the equation. So for me, non-relativistic limit, it means the kinetic energy, is the total energy minus the mass energy, is less, much less than the mass energy. Who control the kinetic energy? This piece. Because, when I do the derivative with respect to time of this, I get the energy, somehow, the kinetic energy, right? The ddt goes like E. So, as I factor out the mass energy, I have only this part, so this part will go according to these things. That means IH d phi dt should go as E prime phi. But this means, because E prime is much less than m0 squared, that this is much less than that. You understand, this is sort of not rigorous things, but just to help you understand. The derivative with respect to t always goes as the total energy, okay, when you do the relation between this operator and the corresponding thing. So here I have factor, and this psi. Here I have factored out already the mass energy. So this object will go only with the kinetic energy. So I expect that it will go like this. Okay, and this is much less than this number. So let's keep this in mind. And now let's keep this in mind. And now let's go on with this, doing the derivative with respect to t and the derivative with respect to x and so on. In the remember in the well, let's put everything to 1, mc to 1, so we have something like that. This is the equation. So we have to do the second derivative. Now from this, we would like to see if we go and end up in the Schrödinger equation. Let's see if this happens. Now, let's start and do the first derivative. So we have to do the second derivative. Let's do the first derivative of this object. So d psi dt is equal d phi dt minus E m0 c square h phi exponential minus IH m0 c squared t. Up to here is very easy. What I did the derivative with respect to t of these. I got this term multiplied by his exponential. And then I did the derivative of these with respect to t, and I got down this piece multiplied by all the rest. Okay. Now, let's do the derivative one more time. Well, first of all, let's remember that this piece, according to the non-relativistic limit, is much smaller than this piece, okay, modulo factor of h. So that means this piece is much smaller than that piece. Okay, so here if I want to be this piece from here, from the non-relativistic limit, is much smaller than the other piece. Forget about the h bar that was in the denominator. It was there. So basically this quantity is basically minus I m square c square h phi 0 exponential minus I h m0 c square t. Okay, if you want to apply immediately the okay, let's you understand this point. So here this object is much smaller than this, so I could keep just this and it would be okay. But let's proceed with the second derivative. The second derivative is d dt d phi dt minus e m square c square h phi exponential minus eh m0 c square t. Okay, so we apply the derivative to all these. Now let's see what we get, but now we start making some approximation. First of all, this object we bring down, let me write the result and then we will discuss it. Now, this piece comes from this derivative. This piece comes from the derivative of this. And why it comes from the derivative of this? Because somehow I have neglected this. Remember that this object is equivalent to this, is approximately equivalent to this. So if you neglect it, you get the derivative of this object plus the exponential. Then I have the derivative of this, okay? I have the derivative of this that multiply all this quantity. You can say, and it is this piece, you can say basically you have neglected a second derivative. Yes, if the first derivative is much smaller than this quantity, if I do a second derivative, here I get a first derivative that is also smaller than this, and so the second derivative I neglected. So here, if you want, I have neglected the second derivative, because if I do from here, the second derivative of phi with respect to t will be much smaller than mc squared d phi dt, but this on the other side is much smaller using this than this, and so on and so on. So I neglected the second order derivative. Now let's see what I get from here, let's sum these things up. You see that you have two things that are equal, and then you have this extra piece. So here I have minus I to m0 square over h d phi dt plus m0 square c fourth over h phi exponential minus I over h m0 c squared t. Okay. Now let me go on this side. Okay. Now just a moment, because I don't see. Now let's rewrite this last piece. I should have 1 over c square e to m0 c square over h d phi dt plus m0 square c square h square phi exponential minus e over h m0 c square t. Okay. Now let's remember which was the okay. Let's remember the original equation. Okay, and let's insert in the original equation the expression we had for psi, that psi r of t was phi r of t exponential minus I h m0 c of t. Okay, now, what did you say? Why did I put a 1 over c squared? To cancel, now, let's see. mc square. I just multiply by this overall factor. Because I need in the next step, I can always do multiply by a factor. I need in the next step, let me remember now how we do the next step. So I have first order derivative. Just a moment, okay, because I think in my notes I wrote it the wrong manner. Just a moment, please. Yes. Now, what did you say?
So there is a 1 over c squared in the equation that
No, I am looking at this. I am looking at this right-hand side. Okay, and then I insert a 1 over c squared. So I have a 1 over c squared also here. You see, remember, this is the second order derivative. This is the second order derivative.
yes, I agree with this derivative, but why did you put 1 over c squared since you don't have it in our equation?
No, but I calculated this quantity. Now I multiply this quantity by a 1 over c squared.
But the equation that we have is t by t squared minus 1 delta squared sine
but you can always have a c square here, you know. I mean, it depends how you look at the equation. Don't be so rigid. I mean, if you look at the equation, look at the Klein-Gordon equation, okay? Let's look at the Klein-Gordon equation. And in the Klein-Gordon equation, if you have the book, is 122, is 1 over c squared, the second derivative with respect to t squared, minus the Laplacian square, the spatial Laplacian.
It's 1 over
C squared, t squared, dt squared. That is the Klein-Gordon equation, you know, because the Klein-Gordon equation we wrote in this manner, okay? And here we have, and this one, this is CT. You understand? So that is the reason. I don't like to get out of the mainstream, you know. I understand your point.
No, we have, because the equation that we want to solve is this one. So
Yeah, no, but the one I wrote there, I said, let's put C to 1. That one I wrote, that one I wrote there, I said, let's put C to 1. You know, let me give you a criteria, because I think, I mean, as you are a student, you are, as I said, you have to understand the substance of the things. That means the core of the things. That is very important. If you keep saying, oh, there is a C, there is a -1, you know, you don't get the core at the end. At the end, you can go back and redo the calculation and fix the C. But it is important that you get to the core of the things. That's, I mean, I insist on that, because otherwise I keep getting interrupted and I keep, that's fine that you fix a C, a minus, and so on and so forth. But, you know, then you lose the main things. It's like having somebody making a speech and saying, oh, but there you have to put a comma. And he's doing a speech, so, okay, I put a comma. And, you know, fine, it's fine that, but it's just the, I want to get to the main result. Then you go back at home, or I go back, and you, at the end, so I would prefer that you keep and don't interrupt till I get to the end. Then you can say, why there is a C there? Why there is, you understand, this is just a matter of communication between me and you, otherwise we lose the thing. Now, here we have 1 over t squared. I put a 1 over c squared, so I have a 1 over c squared. Here, minus 1 over c squared, minus 1 over c squared. I have added. Then I use, now, as on the left-hand side I have a second derivative, I use this equation. So basically all this quantity that we have obtained is minus 1 over c squared, the second derivative of psi with respect to t squared. Okay, let's use now the full equation. That means now I replace this with the space part, because I have the Klein-Gordon, so I replace this with the space part. And then look what I get. So here I replace with the space part, that means it's something like this, okay? Plus the mass term, there is put c equal to 1, put the correct sign, and so on and so forth. So I replace this with what the Klein-Gordon equation tells me. And the result that you get is, there is a part here with the mass that cancel exactly this part, and you are left with this second derivative and the first derivative. You understand the point, okay? So I've started with this. Now here, for this, I use the Klein-Gordon equation, minus m squared, c squared, or let's put c equal to 1, psi, and so on. Use this, and then what you get is actually, there is something get cancelled, is a plus. But there is a minus, so if there is a minus, it gets a plus, it cancels with this. So this part cancels with this, and you are left only with the space part and this. So summarizing, you understand that this is the important things to grasp, that I have used here and here, I have used the relativistic limit. The relativistic limit tells me that d phi dt is much less than m square c square phi m0 c square phi. Okay, and this is the relativistic limit. And there is an h bar and so on, but it doesn't matter. So what I replace this with this spatial part, and I do because I use the Klein-Gordon equation. There is an extra term that cancels with this. What you are left with the space part and the time part. You collect all of them and you get 1 over h d phi dt. Also this part gets cancelled because there is a factor in front, equal minus h squared over 2m0. Then you have this part that is d second dx squared plus d second dy squared plus d second dz squared phi. And this is the usual Schrödinger equation for phi. You see? You can say, oh, but it's not the Schrödinger equation for psi. Yes, but you know we have factorized psi in this manner. Psi equal phi exponential I minus m0 c squared t. That means we have factorized the part that is really the mass part, that is the relativistic one, and we got the Schrödinger equation. Okay, so this c squared cancel with this c squared, you see. Then this c square, here I have an m square, c square, h square that cancel with this piece where there were all the h square. I have used the Klein-Gordon equation. So what is left is only this piece, that is this. Okay. Okay, so that is the correct relativistic limit. Now this, if you want all the proper factor, is what we have done is page 7. Okay, is page 7 of and 8 of the book. Okay. Now one can say this particle and this equation that we got, so this is the non-relativistic limit and this is the Schrödinger equation. This one, does it describe a particle with which feature? Is a particle with mass m0 and spin 0. You remember that if you want to describe in the non-relativistic limit a spin 1/2 particle, you need the Pauli equation. You have done the Pauli equation, I imagine, in quantum mechanics. And the Pauli equation has two, is a wave function, is a couple of wave functions. Remember, the Pauli equation is written in this manner and is an equation for two components. Here we have only one component, so for sure this describes a spin 0 particle. So we got the non-relativistic limit of a spin 0 particle. Did we do something about the spin above? No. So also the Klein-Gordon is for a spin 0 particle. Okay, we did not do any manipulation on the Klein-Gordon except taking account of the non-relativistic limit. Why I'm telling you this? I'm telling you this because sometimes people say that the spin is a relativistic effect. You find some old book where there is written these wrong things. It's not, absolutely. The Klein-Gordon is a relativistic equation, but it describes spin 0 particles. So the spin, they have in mind that because the equation that is used most is the Dirac equation, and we will see that the Dirac equation describes spin 1/2 particle. Okay, so if you find in some book the statement the spin is a relativistic effect, they refer to the Dirac equation that we will do later on. But up to now, the Klein-Gordon describe a spin 0 particle. Now, let's do one thing, and let's go back to the now. Okay, so the free, I mean, why the Klein-Gordon we can somehow say is not a wrong equation. is not a wrong equation because it's not relativistic limit, is exactly the Schrödinger equation, so somehow it is okay. It has the problem of the probability interpretation fails. Now, and so that is a big problem. Let's work on that a little bit, and let's go back to the free wave solution. Okay, if you remember, so the non-relativistic limit is done. So let's go back to the free wave. The equation was this. And equals 0, and P mu is IH ddx mu, where x0 is CT. Okay, so that here there is a C, and when you do the square, there is a 1 over C square in the denominator. Now, we have seen that psi with some normalizing factor exponential minus IH P mu x mu, and we use the Einstein convention that when the two indices are crossed, it means sum. This one, if we write in component, is exponential 1 over h bar p times x minus et. And why see this? Sorry. Why C disappear is because P0 is E over C, and so C cancel, okay? Now, we know that for this solution, this free wave solution, for this free wave to be a solution of this, P and D have to satisfy the usual energy relation and mass energy relation that was the following: E square equals C square P square plus M square C square. Okay, that is the same as I have brought on the other side for this simple reason. So this is a solution of this equation only if E and P satisfy this relation. And then if you take the, which given P, and this is the three-dimensional P, okay? A given P, which is the energy, then the energy associated to some P can be of two types, plus and minus C, M square, P square. Okay. So the solution, as there are two energy, remember this is a solution only if E is not a generic E, but is EP, the one that is solution of this equation. Then there are two solutions, plus and minus equal exponential I over H P times X minus E, and here there is plus and minus, so let's put this is EP plus and minus, EP plus and minus T. So you see that there are two solutions. Now let's go back and see what happened to the probability density. If you remember what we call probability density, even if it had no meaning of probability density. Okay, let's go back to the probability density. Okay, the probability density was rho IH to M0 C square psi star d psi dt minus psi d psi dt. Now let's suppose that our particle, that the particle we described with mass m, has a charge. And let's then introduce a different object that is rho prime, that is the probability density multiplied by the charge, okay? So E is the charge. Then, of course, you have the analog also, the current density. Now with E is E H bar to N0 psi star psi minus psi C star. And now this is not a probability density, but is a charge density. Because I have multiplied by E. If I interpret that as a probability density, even if there were a problem, multiplying by E, I have the charge density, and this is the current. The charge current density. Then, you know, things might now get fixed. Why? Because as these new quantity are really charge density, it means, as it can be positive or negative, that this Klein-Gordon solution might just be either a positive or a negative charge density. That means it can describe either a positive or a negative charge particle. Let me tell you what is eventually the things we will do. You see, the psi, you know, it looks like a wave function, but you can interpret also as a field. When you did electromagnetism and introduced the mu xt field, what is a field? A field, after all, is some function of x and t, and also this is a function of x and t. So you can interpret the wave function as a field, as a particular field. And you know, the fact that usually is interpreted as the charge is interpreted as a probability amplitude. It was good in non-relativistic mechanics, but here we have already trouble. So it's much better to interpret the psi of the Klein-Gordon as a field. And this is a sort of classical equation in the sense that this is a field, but we have not quantized this field. Okay, we have quantized x and p and got this momentum, but we have not quantized psi. So we can say that this is a classical equation for this field that we have not quantized. Psi, we have not quantized. Okay, let's now go back to the, given this interpretation as a charge density, let's go and see, here we have two solutions. Let's go and do the following things. Let's insert this solution, let's insert into here. It means we take for psi plus and psi minus and insert. And what we get is, of course, as we are two solutions, we will get two rows. We get a plus and minus equal plus and minus E, EP modulus over m square c square psi plus minus star psi plus minus. Note, now we have put in the free waves, just a particular solution. But on that particular solution, you see this is positive. And if this now is a charge, it is plus. For the psi plus solution is a plus charge. Okay, so this is a charge density, but it's a positive charge density. And for the minus is a negative charge density. Okay, just do this simple calculation. It's very simple to take that expression and put it here. So we can now give a different interpretation. Psi plus as a free wave describe a particle that has plus charge, plus 1, plus E. The minus, the psi minus, describe a particle that has minus charge minus E, you see from there, because the probability density is really positive, because this quantity is positive, but the one associated with the psi plus as a plus here, so is a positive charge. thing. So these two solutions, at least for the free waves, describe particles with different charges. And we don't have to go back anymore and say, oh, well, in the Klein-Gordon, we have positive and negative energy, where the negative energy was a particle with a negative mass is something very strange. Dirac tried to give an interpretation, but it was not really much accepted. So it's much better to have this, that the Klein-Gordon field describe system that can have plus or minus, so that means the rho is not ambiguous quantity anymore, at least for the free waves, is not an ambiguous quantity because it's either positive definite or negative definite, and having put this is a different object, we have multiplied by this quantity. Now the question that you can ask is, okay, well, let's do things precisely and let's calculate the normalizing factor A. Yes?
Okay. What about if we have a particle with no charge?
No charge, okay. I was getting to that point. You know, you get things with charge 0 if psi is real. You see, if psi is real, this is 0, right? So all you get, you cook up a solution that is real. How do? You sum psi plus with psi minus and get a cosine or a sine, and that is a real quantity. Okay, so linear combination of these produce a particle with charge 0. So it can describe also system with charge 0. Now let's, please.
When you write the Klein-Gordon equation, we are not talking about charge, right?
Right.
Then we came out with something related to charge.
Right, okay. I mean, for sure, the Klein-Gordon describe a particle with mass m, with spin 0, okay? But nobody forbids us to say that, let's suppose that the psi can have associated a charge. Let's suppose that means, and then we see that it can have both a positive charge and a negative charge. I mean, we are just saying, when I made the things about that is a field, don't associate anymore like with the Schrödinger equation that psi is associated to a particle. No, psi is a field now. Okay, so if it is a field, that field can have different charges. It can be, you know, for example, this one has no charge at all. The Klein-Gordon field, we say that it can have a charge, but it can be both positive and negative. Okay, so then we can say, look, the Klein-Gordon equation can describe both positive charge particle, negative charge particle, but also zero charge particle. So it has the room, because of these plus and minus, it has the room to get another quantum number into it, okay? That is the charge. And does that answer your question? Yeah, you see, the point is this, you will understand these things very carefully, much more carefully than these, when you do what is called second quantization that you will do next year. The second quantization means that this that is a field get quantized. You can say, what does it mean that the wave function gets quantized? No, look at it as a field. You know, when you do the point particle, the analog of these is Q and P, right? Q and P are the analog of the field. Okay, so as we quantize these, turning them into operator, we can quantize these, turning them into operator. And the same we will do. You will see when you do second quantization, you turn the wave function into an operator, okay? And then if you turn into an operator, you see that then this equation does not describe only one particle, but it describes many particles, a system of many particles that can be either positively charged, negatively charged, or even neutral. Okay? In fact, if you remember, I told you, this description does not allow you to describe, if you stick with single particle interpretation, then you have to stay, the localization length is at most the Compton wavelength. If you want to go below, so that means that delta x is less than the Compton wavelength. If you want to go at a slower, if you want to increase the resolution, then what will happen, you have to give more energy, and then you will create E plus, E minus couple, okay? And the other day I explained a little bit. You see, then it means that actually this system, if you want to have a resolution at any scale, not just at the Compton length scale, has to describe something that contains more than one particle, like couple pairs and so on and so forth. And the right framework is second quantization. But we will not go into that for the moment, not in this course, okay? Yes?
For now, I'm familiar with the charge and the spin, and I saw it describes charge and spin. Is there another thing, another thing like, other than charge and spin that's described by the Klein-Gordon?
Well, yes, there are, no, for the Klein-Gordon equation there are not, but you can have, you know, this is the wave function. Without putting anything, we know that it has mass, spin 0, charge. You can have other quantum numbers, like, for example, isotopic spin and so on and so forth. Then what you do, you put a label here, A. It means one wave function describes a system with some quantum numbers, like for example, isotopic spin. You will see what is isotopic spin, maybe you have done in some courses. For example, the proton and the neutron belong to a doublet on which one has isotopic spin 1 and the other has isotopic spin 0. So there are other quantum numbers. But to get them in, you need to put a label. So as we have not put any label, then there are just the three basic things: mass and energy, momentum, we know, spin, we have not put indicated anything, so it's spin 0, and charge. So if we don't put any label, these are the three features that it can have. But if we want extra number, then we have to put a label. Okay, now let's do here we have two solutions, so we should put two coefficients, A plus and A minus. And let's see now if we can get it, if we can calculate it like we did with the Schrödinger equation. So it's a very simple thing. What we do is we work in a box. Instead of working on all the space, we work in a box. Okay, so this is X, Y, Z. Let's work in a box with side L. Okay, and let's calculate A plus using the normalization. Of course, I mean, or if you don't want to use normalization, let's remember that rho prime was the charge density. So if I integrate, and I have told you one has a positive plus charge density, the other has minus. So if I want the total charge, I integrate the probability density over all, and I know that it can be plus or minus E. That means not it can be. I impose, as this at the meaning of probability density, I impose that when I integrate over all the volume, I get the total charge, and that charge, the smallest unit of charge is the charge of the electron. So I impose, this is my normalization condition. Now, why I cannot do anymore rho d3x equal 1? Because this has not the meaning of probability density. So the normalization condition for the Klein-Gordon are these. Now, I don't know in the final exam, but I might put beside a couple of problem or whatever, some minor question like this is one that I might put, which is the normalization condition for the Klein-Gordon equation in a box, and everybody says psi star equal 1. No, because psi star does not have the meaning of probability density. The normalization condition is this. The only object that makes sense is the charge density, then the integration of the charge density over the volume has to be the charge, and the charge we have seen can be plus and minus E. So, yes? Yeah, but we can get it out of these two. We can get as linear combination. You know, if this is a solution, also linear combination are solution. So we can get a linear combination of a charge plus with a charge minus, and the overall wave function describe a particle with charge 0. Okay, so now I am normalizing these, and these are exponential, not sine or cosine, so they are not real, so they have charges, this one. Okay, now as we are inside the box, we know that the wave function we are inside the box with infinite wall somehow, so that means we want that the wave function goes to 0 on the wall, and then this tells me that the P, you know, remember, we want that this psi plus, psi minus is 0 on the 3 walls, on the 6 walls that there are. And then what you get is that Pn as a vector is 2 pi over L n, and n are triplet of integer number, nx, ny, and z. This is the analog in 3 dimensions. Sorry. This is the analog in 3 dimensions of the usual quantization on the momentum, because I want that at time t equals 0, so I put 0. I want that in 0, in L, and so on, this is 0, and then it has Pn has to be an integer like this. Okay, then immediately you get which is E. E is from here, and it depends on P. So you get that Pn is equal C plus minus Pn square plus M0 C square. Okay. Okay. And this is equal plus minus C, and then 2 pi L Okay, so you see that also E is labeled by integer, this set of integer. Okay, now let's put this expression and this expression inside here. So now we have a Pn and we have a EPn. Okay, and also this is labeled by n. And now as integration over the volume you know is L cube. We have to put in the expression of rho. So let's put in the expression of rho that we had. I don't want to rewrite it anymore. And then we get the following things. L cube d3x rho plus minus x. What does it mean, rho plus minus? I put in either the solution plus or the solution minus, and I impose that is equal to E plus. Now, rho is made of psi and the derivative of psi, and I know here. So now this expression, the only things that I have are the integer, and if you do this calculation, you get plus minus E EP M0 C square A n plus minus modulo square L cube, it must be equal to 1 plus E, and from here you get the normalizing factor. You get the normalizing factor AM plus minus are equal to M square C square L cube E Pn. So they are the same for plus and minus. Okay, and the wave function, having obtained, so you understood how we obtained the normalizing factor. Okay, I did not do all the calculation, otherwise I would have. Now from here I get the solution. The solution have this form. Now I put in this expression, m0 c square L cube E Pn exponential I over h bar Pn times x minus plus En times t. So the difference, note the difference here is only in this object that there is a plus and a minus, because the energy can be plus or minus. Okay, so the only difference in the two solutions, the coefficient in front, the normalizing factor is the same, this is the same, the only difference is here. So the plus and minus of the two charges is reflected here. Now, in general, now I can do linear combination of them. Let me cancel it somewhere. Let's cancel here. Yes. Yes, basically I remain in general with a plus minus, and then I prove that actually they are the same. The A plus and A minus are the same. I proved that they are the same. No, in the exponent here there is a plus and minus. I forgot. There is a plus. There was in fact minus for the usual one, and then if you change sign you get plus. I mean, the usual things without looking at the sign of E is minus ET, is PX minus ET, okay? Then if you get a negative things, you get a plus, because negative energy now, as it is a linear equation, you see the Klein-Gordon is a linear equation. Linear, it means what? That psi enter with the first power, and in fact psi enter with the first power on the Klein-Gordon equation. There is no term like lambda or g psi square. There is only first power, so it's linear. Then if it is linear, you can have linear combination of the solution that they are still solution. So for example, you can have psi plus combination Na psi n plus, where these are arbitrary coefficient, and you can get An. Then we know the form of these, m0 c square L cube EP exponential I over h Pn plus x minus EPn times t. You can do linear combination of the psi minus. Let's call the coefficient Bn. Historically, they are called Bn. This, remember, were the normalizing coefficient. Now, as to answer his question, these are all objects, linear combination of objects that have all charge plus. These are linear combination of objects that have all charge minus. But of course, I can do psi plus minus, psi minus, and here I would get something combining the two most basic one, for example, n and n with the same n, okay, without summing over any coefficient, I get something, if I do the sum of 2, I get something that goes like the cosine. And then this object, this phi, is real. Phi star is the same. Okay, then this is real. Then if it is real, remember that rho prime is proportional to phi star d psi dt minus phi d psi star d phi star dt. Then if it is real, this is charge 0. So you see there is the possibility of describing particle with charge plus, charge minus, and charge 0. A typical example of a particle with spin 0 that come with 3 different charges is the pion. The pion is a spin 0 particle. These 3 roughly have the same mass, so they can be described by the same equation roughly, because there are corrections, but they are due to strong interaction. And we don't care about that. So for example, yes?
Here, what is the physical meaning of n and p, like anonymous?
No, okay, you see this depends on n. So this is the probability, this an is the probability amplitude to find some particle with charge plus, but with some quantum number n. That means one wave or another wave, and the same here, okay? So for example, a system that is described by the Klein-Gordon equation, at least at the free level, is this. They have spin 0, mass different from 0, and they have 3 charges, plus, minus, and 0 as charge. So this is a typical example described by the relativistic Klein-Gordon equation. Now, we will don't have time. Tomorrow, the charged one, we will concentrate on the charged one, where psi is complex, and we will see to divide into a real and imaginary part what happened, and so on and so forth. We will play a little bit more, not tomorrow, Thursday. We'll play a little bit more with this. Of course, you know, in this book there is much more than what we will effectively do, but I prefer to have a book that we follow so that there is no complaint about the notes or anything. But we will do much less than what is in this book, because it's basically impossible. After we will do a little bit more on the Klein-Gordon, then we will go to the Dirac equation. It is the one that is much more used because it describes spin 1/2 particle. And okay.